Hey there, last episode was already pretty long, and I didn't want to push too much information in one video, so part of this one will build upon what was presented in episode 7. If you open the Biome Sample plugin example that shipped with PCG, you might have noticed that when you play the map, there is runtime generation on top of offline generation. PCG Biomes are plugins you can enable, which gives you Biome Core that you can use on your project to design biomes, and Biome Sample that gives you an example of how it can be used. Here I have the biome sample map that you can find under Engine, Plugins, PCG Biome Sample Content, Maps. Make sure you have Show Plugin and Engine Content enabled to see it. I won't present Biome Core features. There is an extensive documentation that is available on the Unreal documentation website, and I'll put the link in the description. The map already have some stuff generated, but if I start Pi, you can see that there is runtime generation. And on top of that, you have grass that have spawned on the trunk of the trees that were generated offline. It means that the runtime generation is reusing data computed offline. In this video, I'll show how we can reproduce this kind of effect and how we can have graphs communicating with each other. As always, the material will be available on GitHub, and don't forget to join the Unreal Source server on Discord if you have any questions. It's a better place to ask for help than the YouTube comments. Alright, let's get started. I create a basic map for this one, as I don't want to put the focus on scale like the previous episode. We'll first see how two graphs can communicate with each other in a very simple setup. So I remove the original floor and add a simple flat landscape. And then I save my map. I'll create the first graph, naming it producer, and drag it into my map. I'll also add an actor tag, producer. This graph will be my producer for data that will be consumed by another graph. So this tag will be useful to identify this volume to get this data. I'll then open the graph and add a get landscape data to query the landscape and a surface sampler to sample it. And if I debug the graph, sample the landscape. Classic. In the PCG graph, you know that there are inputs and output nodes. With the deprecation of the input pins on the input node, like the landscape pin, it's not that much used outside of subgraphs. But the output node has a specific usage for a top graph. A top graph is the graph that is set on the PCG component. Everything you plug into the output node will be serialized on the component. If I plug the results of the surface sampler in the output node, you can see that on the PCG component, under generated graph output, I have an entry with a point data, meaning that this point data is now serialized on the PCG component. I can then create another graph, naming it consumer, drag it into the world, and make it overlap with the previous volume. In this graph, I'll add a getPCGComponent data node that is an external query node like the getActorData or getLandscapeData. For this node, I want to select my actors by tag and look for the tag producer. I'll also check must overlap self, so I select only the actors that are overlapping me. I can inspect the node to check if the node successfully gathered the data from the producer graph. And if I debug the node, it is the same result than previously, except the cubes are now owned by the consumer actor and not the producer. I only want to spawn points that are within the actor bounds. If you remember the previous video, you can use an intersection node with getActorData. But you can also use the call point outside of actor bounds, which do the same thing and is even more specialized, so the calling should be faster. I can then plug it into a select mesh spawner and spawn some trees. This is a very simplistic example that shows how two graphs can communicate with each other. On top of that, now we have a dependency between the two graphs, meaning that changing the original graph would also refresh the second graph. So if I change the points per square meter on the producer surface sampler, it will automatically make the consumer graph refresh with this new data. Please note that this dependency is editor only and on Pi. If you need this kind of dependency at runtime, you'll have to do it yourself and call generate on the second graph after the first one is done generating. Of course, we must be careful with the dependencies, as we can't have the first graph to depend on the second and the second to depend on the first one, because we will have a circular dependency and the generation will fall in an infinite loop. For science, I add a get PCG component data that pulls all PCG volumes in the producer graph. And you can see that I have this infinite loop. Thankfully, I can cancel the execution and immediately remove this abomination. Another interesting feature of the get PCG component data is that you can create custom pins on the node if you know which pins the other graph outputs to. On the original graph, let me change the output node to rename the out pin to 3 points. I can also change allow types to points because I know it will be points, and change the pin status to normal so that the output pin is no more hidden by default. And I'll add a second pin that I will name rock points that will have the same properties. In this graph, I will add a new sampler to generate more points. I will play a bit with the extent. I will make sure that the steepness is 1 for both sampler. Then I want to do a difference between the first point data and the second point data, and plug the results into the rock points. Now if I check the PCG component, you can see that I have 2 generated entries, each of them on a different pin. In the second graph, I can specify in the getPCG component data node the 2 expected pins, 3 points and rock points. If I inspect the node, you can see that I have no more data on out, and I have 1 data on 3 points and 1 data on rock points. And so from there, I can spoon the trees and the rocks. So that's the basics for communicating between graphs. This is already very powerful and can be used for multiple things such as pre-computing information, forcing generation order, etc. etc. Alright, now that we have covered the basics, let's see how we can combine offline gen with runtime gen. I'll remove my 2 simple graph and we'll create another one, offline gen. I'll put the graph creation on Timelapse, as I've done it times and times again, and it's not the most important thing for this video. In a nutshell, I want to generate some points for my trees, scale them up with a random rotation, and play with the bounds for a good exclusion. Since the point are scaled, they can overlap themselves, so I'll add a self-learning node. And for the rock, it's the same, but with the difference node. Don't hesitate to jump to the next timestamp if you want to skip that. I'll also scale my volume up. Now that the meshes are in place, we want to sample points on the tree's trunk, like on the biome sample demo. We saw this in previous episodes. We need to use a mesh sampler. Since the meshes between the trees are not the same, we will need to do the sampling for each of the unique spawn meshes. First, I want to change on the static mesh spawner the attribute name where the path of the mesh will be written to, and choose mesh. If I inspect the node, you can see that I have the spawn mesh path as an attribute for each point. Since we want each unique mesh, I'll use an attribute partition on the attribute mesh to create a 3-point data, one for each different mesh. You probably see where I'm going with this, if you saw the 5.5 new features episodes. The idea will be to loop on each of those point data to use the mesh sampler on each mesh. For that, I'll create a new loop node and create a new PCG graph, 3 mesh sampling. If I double click on the node, I can jump to this new graph. What I want here is an input pin to read my input points that are coming in multiple data. So I set up my input pin to be a pin of type point that is normal and a loop pin. I can recognize the loop pin with this little arrow. And as output, I want to forward my input points into the out pin, but I also want to have another pin that will be the sample 3 points. I'll go back to my previous graph to connect the input to debug to our data. As a reminder, the fat edge means that multiple data are flowing. And if I inspect the input node, you can see in the debug tree list view that I have each iteration of my loop. And for each of them, I will have a unique mesh. From my input points, I want to extract the static mesh to feed it to this mesh sampler. So I'll use a get attribute from point index with attribute mesh and index 0. Since all my points have the same mesh, I can just take the first one. Then I want to use the mesh sampler. As a reminder, the mesh sampler needs the PCG geometry script interrupt plugin enabled. We want the mesh sampler to use the mesh coming from the attribute. To do so, we plug the attribute set into the static mesh override pin on the mesh sampler. For sampling method, I'll use the Poisson sampling one. Since the mesh sampler is sampling in local space, I need to copy the resulting points onto my input points to visualize them. So my mesh sampler will be the source for my copy points, and the input points will be my target. If I debug the copy point node, I can see the points on my mesh. And I clearly want way more points than that. So I'll change the Poisson sampling radius to 2. For faster iteration, I will just scale down the volume a bit. Let's do some math. Since I want to have points that don't exceed a certain height of the tree, I need to know the mesh height. For this, I have multiple solutions. I could use the bounds of the mesh with point from mesh, using the same static mesh as the input data. This actually creates a single point with the bounds encapsulating the mesh. From there, I can extract the z component of the extents. The extents are the difference between the bounds max and the bounds min divided by 2. So they are actually half extents, which means that the z component of this is my half height. To get my height, I use the multiply node to multiply the half height by 2, a constant created with create attribute. So that's one way, but let's try another one, especially when you don't have access to the input mesh. Since I have a point cloud, I can compute the minimum z position of the point cloud and the maximum z position. This gives me the height of my mesh. I can get the min-max with the reduce attribute on $position.z. $position is the position vector of the point, and the .z gets its z component, same as the accent. Subtracting both, and I get the mesh height. You can see that I'm using at last for the operation. At last means the last modified attribute. You can see it in the attribute list view on the top left. And my height is negative because I plug in the wrong way, so I just will swap them out. I can then multiply it by, let's say, 0.2, using a create attribute to define constant. So I only keep the points that are under 1/5 of the mesh height. I can then add this value to the min position, and this gives me my height threshold. Finally, I add an attribute filter to filter my sample points. To tidy the graph, I can double click on an edge to create a remove node. On the attribute filter, the target attribute is $position.z. I want to keep values that are below this threshold value. And the threshold attribute is the value we just computed. From there, I can copy the points again, tidy the graph a bit, and debug the node to see that I have kept only the points that are at a certain height. I can even increase the number of points by reducing the sampling radius on the mesh sampler. To mimic the effect of biome sample on top of that, we can do a linear gradient on scale. So points on the top are smaller than the points at the bottom. Since my mean value is close to 0, I'll be lazy and just divide the height by the threshold. I can then clamp it between 0 and 1, and do a 1 minus. This will assign the value 1 to the points at the root of the tree, and 0 close to the threshold value. I can then multiply it by the scale and store it in the scale. This will make my points normal size at the bottom and very small at the top. And same thing as before, I will use the copy point to see what I've done. And the effect is working. I have big points at the bottom and small point at the top. But I feel like the height of my points is too high. Yeah, so I will probably want to change the height threshold. Yeah, it's better like this. Alright, now that we have done the pre-processing of the points, I can remove the copy points and output the results into my output node. I will put the results into the sample points output node, and I will forward the input into the out pin. If I go back to my top graph, you can see that I have an output, the 3-point data, and also in the sample point bin, also 3-point data. I will then output everything into the output node the same way we did with the producer graph in the first part. And if I inspect the PCG component, I now have 3 entries in the generated graph output. 3 for my 3 points, 3 for my sample 3 points, and 1 for my rocks. Right, the offline generation is finally done. Let's just make the volume a bit bigger to have a nicer background. Let's move to runtime generation. I create another graph named onlineGen, and we'll drag it into my map, place it at the origin, and scale it. Since I want to use hierarchical runtime gen, I'll mark it partition and generate at runtime, and in the graph, enable hierarchical gen and make the default grid unbounded. We'll start by sampling some grass, so get landscape data and use the surface sampler with a high density and small extents. Then I transform points for randomness, and the static mesh spawner with the C-link mesh with no collision. If you remember from previous episode, to see the results, we need to enable the viewport as a generation source in the PCG world actor. And I don't want to generate on the unbounded grid, but on the 800 grid. So I get the landscape data with a grid size node. You've noticed the popping when the generation is happening at the limit of the generation? I greatly encourage you to see how they did it in Biome Sample, using the PCG foliage material and wall partition offset. If I override the material on my foliage to use the one coming from Biome Sample, I have this wonderful smoothing at the limit of the generation. I love it. Alright, always the same song, we are intersecting with the trees and rocks. But this time, those were generated offline, so we don't have access to those in the graph. So we'll need to query it with a get PCG component data node. I also need to add a producer tag to my offline gen module to identify it. Then I can set the actor selection tag to producer. If I inspect the node, you can see that I have all my data, but collapse under the out pin. So I'll set up the node with the expected pin. And it seems I can write correctly since I made a typo in the offline gen graph. So I'll go change it and make sure to force regen while flushing the cache to remove the error. Just as a reminder, to do that, you just do Ctrl plus click on force regen. And now I can use the difference node to remove the 3 points and the rock points coming from my get PCG component data node. Okay, so it removed the grass, but way too much. What happened? If I debug my get PCG component data node, you can see that the bounds of each mesh is way too big. That's because in the static mesh spawner, we have the option that is on by default to apply the mesh points to points. And for the trees, since the top of the tree is way bigger than the trunk, it will make big bounds and will remove way too much points. Since I did the bounds myself before, I will just disable this option. Yeah, not perfect, but it's good enough. Alright, so we have the trees and rocks generated in the editor, and the grass that only appears at runtime. Finally, let's add the points from the trees. We'll get the 3 points and make sure we get them by the 800 grid size node. We then need to copy them. So copy points, right? Unfortunately, in 5.4, copy points is doing a Cartesian product. Since we have 3 data, 1 for each tree, if we do the copy points, we'll end up with 9 data, which is definitely not what we want. You'll have the option to copy each source to its respective target directly on the node in 5.5, but in 5.4, we'll need a loop. So I'll add a loop subgraph and create a new graph. In the input pin, I will set up 2 pins, one for my in points and one for my sample points. Both of them will be loops. Since we are in a partition setup, we will need to call our points outside of our actor bounds. We need to do it inside of the loop, because if we do it outside of the loop and there is no points in the partition, it will remove the data from the data collection and will mess up with our order. So I'll do it inside the loop. We can then use the copy points node to copy the sample points onto the in points. We can then use a select points node to have different patterns. We can select, let's say, 70% of the point. And also a transform point for randomness on the rotation. I can then change the output pin for points and output the result. And in my main graph, I can plug the 3 points in the in pin, my sample 3 points into the sample point pins, and since I want to spawn graphs, I can just plug the result directly into the static mesh spawner of the graphs. So it's working, but it's way too big. So I have to go back to my loop and on my transform point to make sure to scale my points down. And there we have it, the grass on the trunk of the trees generated at runtime. I can press play to go in Pi and see them generate. And that's all for today. Combining offline generation with online generation really enables to pre-compute a lot of things beforehand to reduce the overhead at runtime. I strongly encourage you to also take a look at the biome sample example to see how they organize themselves to achieve similar results. I hope it was useful and I see you in the next one. In the meantime, have fun with the plugin. Take care.